Good evening, everyone. My name is Christina Greb, and I'm the Collections and Education Specialist at the Mining and Rollo Jameson Museums. Today is Sunday, March 17th. Happy St. Patrick's Day, and welcome to our fourth Winter Lyceum presentation of 2024. The next Lyceum will be the last one over Zoom. So next Sunday, historian Robert Humphreys has his presentation on the Welsh in Wisconsin's lead mining region. And finally, skipping over Easter Sunday on April 7th and in person at the museum, I will be giving a presentation on how our collections team helped to preserve our taxidermy collection and the famous boxing squirrels. We invite you to stay up to date on all of our upcoming events and museum programs by checking us out on our website and by following all of our social media accounts. We welcome current friends, members, and donors of the Mining and Rollo Jameson Museums tonight. And additionally, we would like to thank our sponsors whose financial support has made this program possible. Platteville A&W, Inspiring Community, Park Place Senior Living. After the presentation, we have a Q&A section. So at the bottom of your screens, there's a button for you to submit your questions, and feel free to submit them at any point in the presentation. I'm pleased to introduce our presenter for tonight, Billy Fitzpatrick. Billy received his master's from the University of Arizona in 2021 and has worked in the Wisconsin Geological and Natural History Survey since 2020, studying sulfide mineralization in the Paleozoic stratigraphy of southern Wisconsin. Thank you so much for joining us tonight, Billy.
Yeah, thanks for the introduction, Christina. So I'll just get right into it. So I'll be talking today about the formation of the lead-zinc ores of Southwest Wisconsin and some of the insights into that I've discovered through some new mapping that I've done in the Highland area. So for an outline for today's talk, so we're going to start off just by getting everybody on the same page with what are sulfides. I'll be talking a lot about sulfide minerals. Sulfides make up the ores of the lead-zinc district. And then we'll get into a brief history of Southwest Wisconsin and with a focus on the Highland area where I'd done my mapping. And then after that, we'll get into more of the geology, talking about, what the sulfide deposits look like, the lead and zinc deposits, and then try and answer a number of different questions about their formation. So where were the metals making up the sulfide source from, and how were they transported to Wisconsin? Why were the metals fixed in place as sulfide minerals, and why are there ore deposits in some areas but not others? So to begin, just talking about what a sulfide is. So sulfide is a mineral where you have metals and sulfur in its reduced form combined together. And these have been the sources of a number of commodities that have been very valuable to humans, throughout history. And just as an example here, chalcopyrite, copper sulfide on the left, is one of our most important sources of copper, and then pentlandite, nickel sulfide on the right. That's one of society's most important sources of nickel. And so, the lead and zinc minerals that were present and mined in Southwest Wisconsin are also sulfides, and were also valuable. And just like anything of value, humans will always be in conflict over it. And so, this bears on the history of Southwest Wisconsin because, kind of one of the first treaties to establish land rights in Southwest Wisconsin, as the United States was expanding, was the 1804 Treaty of St. Louis. And so this encompasses the green area that I've highlighted here. And so the blue polygon that is also on there is what would become the lead zinc mining district. So you can see how, this treaty was tailored to include that, like they knew what they were doing. And this is widely regarded as a very unfair treaty. It's between the United States and only 5 chiefs that did not have authority to cede this land. And the terms, even if they did, were very unfavorable. And between this and a series of other treaties that were signed in the 1810s and 1820s, this effectively relinquished all rights from tribes to the United States in what would become the Lead-Zinc mining district. So, yeah, with these land rights being solidified, this brought the first big wave of European settlement. And so this is a graph of lead production by date here. And so this black line that I've marked at 1830, you can see this steep uptick in the lead production, with these treaties being signed. And you can see there, right after 1830, there's this very pronounced break in, what this exponential rise, and this corresponds to the Black Hawk War. Yeah, so you may have heard something about this. This is widely commemorated in southern Wisconsin by, a number of roadside historical markers. So, this started early in 1832. So Black Hawk, he was a Sauk chief who was very familiar with the Treaty of 1804 because it had forced him from his home village east of the Mississippi River. And so he had long resented the treaty and regarded it as unfair. And in an act of protest, he crossed over the Mississippi with a band of his followers, hoping that other tribes would join him, in this expedition. And after initial success at the Battle of Stillman's Run, he was chased by a large group of militia that, it became increasingly more desperate until, his followers were massacred at the Battle of Bad Axe in their attempt to recross the Mississippi River. So, with this decisive victory, there was a resurgence in settlement, as basically, there was stability again in the mining district. And so you can see that huge rise there. So you can see the lead production peaked in the late 1840s, and then there's this decline after that. And this is actually due to the California gold rush. So you may know the 49ers. So a lot of people that had come to Wisconsin chasing the lead rush were then taken away, by the promise of riches in California. And even despite this decrease, Wisconsin was the #1 domestic producer of lead from 1830 to 1870, which is pretty impressive. And it shows you how big of a deal mining was for this area back then. And so, yeah, again, this is the historic mining district there in the blue, and Highland was one of these mining centers within it. It's actually the northernmost center of mining that took place, and the blue box there is what I've mapped for my geologic map. So zooming in on that, you can see here, so the blue and the green polygons there, those are underground and surface workings, that were, historic mining. So initially for lead, like I just shown you with those graphs. And, what I think is really interesting too, so this is, a public land survey system, like original map. So this was completed from 1832 to 1833 with a notable gap during the Black Hawk War. And, so this is setting up the initial framework for this land that's being incorporated into the US. And in doing these surveys, they would note some of these cultural features. And there's really not very many. This is very early in the history of the area. But what's really cool to me is that, so you'll see here, there's this place marked Jones House and Diggings, and then Wood's House and Diggings. So when you compare those locations to present day maps, those actually correspond to the two largest areas of mining in this, like in the region around Highland. So these early prospectors, through luck or coincidence, just stumbled upon what would become the two biggest mines around Highland, which is pretty cool. So yeah, kind of getting back into the history. So yeah, there's a sharp drop in the lead production, and then around 1870, 1880, there was this transition where zinc became the primary commodity that was being mined in the district. And so this was a resurgence in activity at a lot of these mining centers that have been operating for a while, including Highland. And so this is a cool photo. So this is from the late 1800s, and it's just a picture of Main Street in Highland. And what strikes me is this really has an Old West feel to it, and it's almost something that's kind of forgotten how much Southwest Wisconsin, the old Lead-Zinc district, like this was kind of the Old West before the Old West. That's kind of been overshadowed. And so these are some slightly more recent pictures. These are from 1919. And so these are pictures of what the mines actually looked like. So this is a smaller one. You can see it's not a very big operation. It has just a small rail track there. It's pretty cool. And then here's an example of a much larger operation. So you can see this is like truly operating at an industrial scale, with a mill and a pretty huge tailings pile. And then, 1919, just as a sign of the changing times, I think this is a really cool juxtaposition between, one of these early automobiles and then, horse-drawn carts in the background on the same roads together. It's pretty cool. Yeah, so zinc production peaked during World War One in the in the lead zinc district, in Southwest Wisconsin. And there's a few peaks after that, but the increasingly, as mines became exhausted and these deposits, when compared to other sources of zinc across the world are relatively small, so they really couldn't compete with many other deposits and mines that were being opened later. And the history of mining in the district basically ends with the closure of the last mine in 1979. So yeah, now we kind of know a little bit of history, but I'm going to show you kind of in a number of steps talking about what the rocks in this area look like, what the ore deposits look like, and then some of the things I discovered in mapping that I think will bear on how they formed. So first off, just talking about the rocks in Wisconsin in general. So this is a bedrock geologic map, and just the pattern that I want to point out is that in the northern part of the state, you have what's called the Wisconsin Dome, and this is exposures of Precambrian crystalline basement. So, over 1 billion years old. These are really old, hard crystalline rocks. And then layered successfully on top of that are a series of Paleozoic sedimentary rocks. So you can kind of see that in this cross section here. You can see the layers that are dipping very gently over at a regional scale. And so in Southwest Wisconsin, this is kind of the sedimentary layers that are relevant for talking about the ore deposits. So you have stuff, it's basically a series of carbonate and sandstone rocks. And, if we take a look at, what the paleogeography of the time was when these were being deposited. So North America, and hopefully you can see Wisconsin here. This was when it was a shallow sea that was tropical, very warm. And so this is what led to the deposition of all of these rocks. And something that's cool about this map too, so 450 million years ago, this is when the Appalachians were in their prime in the eastern United States. Oh yeah, so I should mention too, so in terms of, so these rocks would then become kind of the host for all of these sulfide ore minerals that we're going to talk about. And the first one to talk about that's most widely present, basically in all of the Paleozoic rocks in Wisconsin at trace amounts are pyrite and marcasite. So these are iron sulfides, and they are everywhere in the sedimentary rocks, generally at pretty low abundance. And this is kind of what they look like. So you might not even notice it, but these little clusters, these are the iron sulfides, and yeah, they really are everywhere once you start looking for them. And this is in the St. Peter sandstone in Southwest Wisconsin. And then, so even though like there's little bits of sulfide distributed over all of the sedimentary rocks, there's really only a few specific horizons that localize like large quantities of these ore minerals, and their distribution even in these horizons is not regular as well. So Southwest Wisconsin looking at the same stratigraphic column, it has these different ore deposits going on, that were mined out. But in eastern Wisconsin, even these same rock layers from the same time generally do not contain the lead and zinc deposits. So that's kind of one of the questions. But I'll just be briefly going through some of these different ore deposits at different positions containing different commodities and just talking about what they look like. So yeah, talking about Southwest Wisconsin. So the original source of lead were what are called gash vein deposits, and these are higher up in the section in what's called the Galena Formation. And confusingly, Galena Formation was named because it contains a lot of the lead ore mineral. So this is galena or lead sulfide, which takes this like very characteristic cubic shape that you might have seen before. In map and cross-section view, these gash vein deposits are basically pods of galena hosted along joint planes. So hopefully you can kind of see that, and they form these like elongate pods along them. And taking another cross-section through them as well. So a lot of these take the form of caves, where you have these widened joint planes that are connected to each other with galena deposited on the walls of it, and then the galena on the walls would fall into the caves and the sediment, to create these things that were very attractive for the early miners to extract. So going down a little bit deeper are the pitch and flat deposits, and these were the primary source of zinc, that was exploited later in the mining district's history. And what these look like are a series of banded veins. And so this one here, you can see, here's the wall rock, which is carbonate, and then you have iron sulfide, and then a thick zone of the zinc sulfide or sphalerite. And this was the ore mineral. And looking at them at a larger scale, so the pitches and flats are what's making up. So the pitches are the incline fractures filled with the ore veins, and then the flats are the horizontal fractures with the ore veins, and they would often come together to make these elliptical interconnected series of fractures that are like the early workers said that they look kind of like the sagging that occurs in a brick wall when its foundation is collapsing, which I think is a pretty cool comparison that fits pretty well. So this is the third concentration of sulfide minerals in the sedimentary rocks of southern Wisconsin in general that I'll talk about. So this is called the sulfide cement horizon, and it's an area at the top of the St. Peter. And it wasn't mined because it generally only contains iron sulfide minerals, but it is very important to water quality, and this is what in large part is causing the arsenic contamination issues in eastern Wisconsin that you may have heard of, because this layer, unlike the ore deposits we were talking about, extends all the way into eastern Wisconsin as well. And this is what it looks like. It's these kind of lumpy clusters of iron sulfide minerals, sometimes filling burrows in the host sandstone. Yeah, so now we kind of know what the ore deposits look like, and where they are in the stratigraphic section. So now I'm just going to talk a little bit about my mapping work in the Highland area, trying to create a geologic framework that would help me to explain how those different concentrations of sulfide minerals formed. So again, this is a map of the Highland area, and I'm going to zoom in to kind of a little case study in the south there that demonstrates something with mapping the process of mapping I think very well. So you can see here, this is a small tributary of the Blue River, steep hills on all sides of it and a quarry on its northern side. So what you might notice if you're looking real carefully is that there's a slope break on the hills, flanking this river. And so you can see here, it's almost like there's a scarp where it drops off very steeply. And so I'll show a picture next from this perspective facing this hill. And so, yeah, what the scarp looks like, is very distinctive. And as a geologist, when you're driving along looking for that, or looking at that, this this slope break implies a change in the resistance to erosion between different layers. And so, thinking back to your stratigraphic column and knowing how things are layered, you can assign that to, like, basically that it's representing one of these contacts. And in this case, this is the top of the St. Peter. And so if you're driving around and you see a steep scarp and then blocks of sandstone below it, you're more than likely looking at this contact. So it's kind of fun if you want to look out for it yourself. And so then combining those sorts of observations and interpolating between them using the landscape as a guide, you can expand these contacts to create a geologic map. And this is like a snapshot of the finished geologic map. And then as another example here, so this is from the Blue River itself in the western part of my mapping area. So yeah, this is a super beautiful, this is the Snow Bottoms natural area, which I highly recommend that anybody check out. And I'll be showing a panoramic view that encompasses that semicircle that's on screen there. So in trying to interpret this view, it's kind of, it doesn't fit when you think about kind of that layer cake, like, flat layers of sedimentary rocks that I had described previously. So you might notice on the left here, there's a very pronounced ridge, and then that completely ends. And then you have these two prominent points of what appears to be somewhat different rock. And you can see the vegetation is different as well. There's pine trees clustered on the top of these things where they're not nearly as abundant on this ridge line here. And so zooming into them, you'll see that these are sandstone points at the same elevation as a big ridge line of carbonate rock. So what this is due to is that not all of the rock units are perfectly flat. So in between the deposition of the St. Peter formation, the sandstone, and the underlying Prairie du Chien group, the carbonate rock, there was a long period of erosion, which created these valley systems and big sinkholes that were then filled later by the sandstone. And then when you see this in the landscape, though, this previous topography, that was developed hundreds of millions of years ago, is now superimposed on the present landscape, and so you end up getting these amazing cross sections that allow you to see into that that old landscape that's now buried. And so, yeah, when you plot this out on a geologic map, these valleys sometimes connect, and you can almost imagine rivers flowing, back in the Ordovician when these rocks were being deposited. Yeah, so putting all that stuff from the map together, you have to put those observations in context to how the ore minerals were forming, and just to give you a very simple model of how any sorts of ore deposit can be formed. It's represented by this this flow chart here. This is a very simple way to think about it. So generally, and this could be applied to anything, but generally you have a source that has something that you're interested in, but it's at too low of a concentration for you to economically extract it. So what you want is the element that you're interested in from that source to be picked up and transported to a different place that we call a sink. So this is a physical or chemical trap which fixes what you're interested in place at higher abundance, that then you can extract that. And so, yeah, I'll be talking about the source for the metals that then went to make up the lead and zinc deposits of Southwest Wisconsin. So Yeah, going back to the Ordovician, so you'll notice Wisconsin there, it's a very shallow sea, but there's these deeper areas of sea in what is now the United States. And what I've highlighted there with the blue circle is what is called the Illinois Basin. So this is an area that is accumulating much greater thicknesses of sedimentary rocks than Wisconsin is during the same time period. And the effect of this is that you're burying the rocks and the fluid contained within them to great depths and heating that fluid up. And this stuff, it's hot, it's very salty, and sulfate rich, and it has metals. Basically, the salinity and high temperature of it promotes these metals going into solution. So the lead and zinc are then enriched within the fluid. And the transport steps, so you have to mobilize that fluid from deep within the basin into the area that is now Wisconsin. And what likely led to this was so now we've jumped forward. This is a paleogeographic map of the Permian, so around 280 million years ago. And at this time, there was a huge mountain belt in what is now the eastern and southern United States that was associated with the formation of Pangea, which had completed by this time. And you can see how close the Illinois Basin is, which I've marked on there, to the front of the mountain range. And what this mountain building event ended up doing. So you have this thick section of sediments within that zone, and you have this ramp leading north on into Wisconsin. So yeah, here's the cross section here through the Illinois Basin that's being represented here, and you're effectively jacking up this side of it. And if you can imagine, that would cause these brines to spill out into what is now Wisconsin. And I have a overly simplified analogy for this too. That's kind of silly, but it might help you visualize it a little bit more. So picture this basin, kind of like a hot tub, bathtub that you're going to fill with sand. You're going to top it off with a little bit of water, and you're going to put a tight cover on it. And then with this mountain building event, you're going to tilt it up. You're going to tilt one side up, and you can imagine the water that would be draining out on the lower side. And that's effectively what is happening when these brines are migrating into Wisconsin. Yeah, so now you have this transport step accomplished. So now we have to think about how to fix these things in place and how to create the sink. So one aspect of creating this sink, that resulted in the deposition of the ore minerals in Southwest Wisconsin are this sulfide phase, the special sulfide phase that we're going to call framboids. So this is an image of a framboid on the right being compared to just a regular grain of marcasite on the left. So you can see we're at a very high magnification. This is an electron microscope image, and you can see it's this cluster of tiny little grains. And the reason it's called a framboid is because it's from the French for raspberry, which you can kind of see the resemblance. But the deal is that people have recognized these things from a long time. For a long time, they're very distinctive, even though they're small in scale, and they're widespread in sedimentary rocks. And people didn't really know what their origin was. But recently, researchers have discovered that bacteria have an essential role in the formation of these framboids. So this is a sample taken from deep well water within a gold mine. So we're talking like kilometers down in the earth, in hot waters that are loaded with the same sorts of things that, the brines that I'm talking about are. And so what you're seeing there around this form that you might recognize as a framboid is this biofilm that appears to be controlling its development. And the bacteria making up oh yeah, and I'll just share a few more pictures of this. This is really cool stuff and pretty new research. So the bacteria that are making up this biofilm are what are called sulfate reducing bacteria. And so these can convert sulfate, which is sulfur in an oxidized form, into sulfide, sulfur in a reduced form, by using it as part of their metabolism, similar to how we would use oxygen. And so these bacteria generate reduced sulfur, and this result basically they're doing their thing in the sedimentary rocks. And when you hit those rocks with a big wave of brine that has a bunch of metals in it, those metals will react with the reduced sulfur to create sulfide minerals. And then that's part of how you wind up with an ore deposit. And yeah, when you look at the lead zinc ores, so this is I'm going to show you some electron microscope images from a sample of zinc ore from the Gutenberg member, which is in the Decorah Formation. This is it's part of the same stack of sedimentary rocks I was showing you. So this is one of the primary ore horizons. So you have zinc sulfide as this brighter color, and then iron sulfide is this slightly darker gray color. And when you zoom in on these sulfide minerals, you'll recognize these rhomboidal shapes, that I've been talking about. So what this tells me is that bacteria, these sulfate reducing bacteria had a key role to play in the formation of these ore deposits in preparing the sedimentary rocks, for further sulfide deposition. And yeah, next I'll show you. So this is an image from Eastern Wisconsin that I love to show because, these same sort of processes are creating sulfide deposition in Eastern Wisconsin as well. Utilizing like the same process, it's the rhomboids, the sulfate reducing bacteria, that are creating later generations of sulfide deposition around them, which is really cool. So these look like sunflowers to me. Yeah, just really cool. You can see when you zoom in this far. And so, I had previously mentioned, so the sample that I'd shown you is from the Gutenberg member. So this is classically called the oil rock by the miners, and this is one of the primary ore horizons. And it's actually so organic rich that you can light it on fire, which is kind of crazy. If you find a chip of this stuff, it's these brown shale layers. If you take a small chip of those, the miners had recognized for a long time that this stuff is associated with the ore, and when you find this organic rich shale that burns, like that's one of these signs that you're onto a good ore deposit. Yeah, it's pretty cool. And why this is important though is because these bacteria, like anything else, they need a food source to metabolize the sulfur and the organic matter within horizons such as the Gutenberg were very important, in helping that process go along and resulting in the deposition of sulfides. All right, so yeah, now we're kind of on to some of the processes that led to the ore being where it was. So we're kind of developing a model for the sink now. So you have these organic rich formations with reduced sulfur, and then what this effectively ends up doing is that you're creating these ore deposits with several percent of zinc. But when you think about the basin sediments that these fluids were sourced from, only having like parts per million of zinc, like that represents this crazy upgrade, like over 1,000 times upgrade in the elements that we're interested in. So yeah, it really kind of emphasizes how special some of these processes that create ore deposits are and how cool they are, at least to me. So yeah, now we've established how to make a sink, but in order to create the largest ore deposit possible, we're gonna have to focus a very large amount of these basinal brines into that specific horizon. So I'm going to talk about a couple of different ways that we might be able to do that. So the first one are structural zones. And so just like to give you a conceptual model of what these represent. So, structures, these are folds and fault zones, that are warping the sedimentary layers that I'd mentioned before. And in the overly simplified analogy, what you can think of these as doing is creating zones of vertical permeability. So these are pathways for these fluids to ascend, upwards. And, getting back to the analogy, this would be like if you took a knife in your hot tub with the cover and stabbed a hole through it. And then that pathway that you've created is short circuiting, where the stuff would be running out at the bottom. So you can imagine how it would jet through that new pathway you've created. And thinking about what we have to make that pathway through. So the Microtextural group is this thick section of shale, and it's found just underneath the Niagara Escarpment, primarily in eastern Wisconsin. But it would have, at the time the ore deposits were being created, have covered the entire state. So this would have been present in southwest Wisconsin as well, and but currently it's only present underneath some of the mounds, such as like Blue Mounds or like the Platte Mounds or Belmont Mound, because the landscape has been eroded more deeply in southwest Wisconsin. And so, yeah, getting back to the Highland area. So if you remember, I'd shown you how to map that scarp in the past. So by mapping that scarp and then tracking its elevation over the entire area that I mapped, that allows you to create a surface for how the bedrock units are being folded. So it's like you can see the elevation of the up and down warpings of the sedimentary layers, that were originally deposited almost flat. And so this is basically the topography of that surface. So you have low areas in the darker colors and high areas in the lighter colors, and the axes of the folds, so the down warpings or synclines, and then the up warpings or the anticlines, marked by these red lines. And so what you'll see here is how closely a lot of these areas of mining are to these fold zones. So this is showing you that these are important for localizing the flow of these basin, these brines that are coming through, in order to get enough volume to make an ore deposit. And yeah, so another way, so yeah, in thinking about how to continue to localize more and more upward flow, of the brines into the critical ore horizons, where the sulfides are being deposited. There's another way that vertical pathways were created within the sedimentary section. So I'll be talking now about what's called the base St. Peter unconformity. So this is what I had talked about previously, that was exposed very nicely at the Blue River. So, creating, when the Paleozoic group, this carbonate rock was weathered, so not only did it create these large scale valleys that were filled with the sandstone, there are also a number of caves and cavities also associated with this weathering event. And a lot of these are visible today. So this is actually at Snow Bottoms, in that cliff face made of the carbonate rock. There's a cave that you can walk into that's really cool. And another example of these karst cavities, that you can see very, very easily at the surface, is in the spring zones. So the Paleozoic group has large springs in it in many parts of the state. But one that's very popular to go to here in Highland is called Big Spring, which is it's a little bit northwest of the village, underneath that red dot. So this is what it looks like. It's huge. So you can see the spring channel pouring with the vegetation growing around it that's feeding into this small tributary of the Blue River. And you can see it's like, where is all of this flow coming from? It's just like a dry hillside. But when you go up to the head of that channel, you'll see that there's a pool of water that appears to be just exiting the hillside. And I think the most plausible explanation for that is that there's basically a cave, behind, maybe a collapsed cave, in the hillside behind there, that is this wonderful conduit for groundwater draining under gravity to come out and form this channel here. Um, the thing is too is that you can, by knowing the discharge of this spring here, you can actually calculate how much metal that would have carried when it might have operated in the opposite direction. So it's a conduit now for groundwater draining out. But when the ore deposits are being formed, it's the same deal. Water's draining under gravity could have used the same sort of cave system as a way to ascend upwards in section. And yeah, just what's cool is that um, so basically there's some estimates on how long the ore forming event might have taken place over. Estimate that I've heard is about 500,000 years. And when you take the discharge of this feature, which is only about, it's like, I think it's less than 2 feet per second, like cubic feet per second, which doesn't seem like much, but when you multiply that over 500,000 years with a reasonable concentration of zinc, this leads to the transport of like 1 million tons of zinc, which is more than is contained in even the largest known zinc deposits in the area. So it's showing you that a ton of metals are being moved through this region during the basin, during the brine migration event. It's pretty cool. I think it also um, it's important for showing how the process which fixes the metals in place might even be more important than how much metals are coming through. And but anyways, so if you that's just one cave, one karst cavity in the Prairie du Chien group. But when we're talking about the paleo valleys, these big valleys filled with the permeable sandstone, this would operate at an even larger scale, allowing these brines to migrate upwards in section. Um, and so taking a cross section through my mapping area, so what you end up seeing is that there's these very simple flow paths, going. So here are the St. Peter, here's a St. Peter Paleo Valley in the, like in the area of the Blue River. There's another large St. Peter Paleo Valley that I've mapped on the eastern side of the mapping area around the Otter Creek Valley. And if you can imagine the brines ascending through these areas with the permeable sandstone, and then basically being trapped in that sandstone until they encounter a fold zone, which creates these breaches that they can further ascend upwards through. These flow paths actually that you can draw between these two areas of vertical permeability, they correspond almost exactly to where you end up seeing the ore deposits found in this area. So yeah, you can see there, this area of the cross section has significant mineralization around it, and that corresponds to where these brines are coming up and out through the sedimentary rocks. All right, so yeah, that's pretty much, yeah, we got through everything. So just wrapping up with a few conclusions. So I think what I found doing this mapping work, looking at stuff under the microscope, shows that sulfate reducing bacterial colonies were important because they basically they created this source of reduced sulfur that could react with the basin brines and precipitate sulfide minerals to form the ore deposits in southwestern Wisconsin. And basically, yeah, several different mechanisms worked to create larger concentrations in very specific areas. So number one, this is the organic rich rocks like the Gunberg, the oil rock that I'd shown you previously, which the bacteria can use as a food source. And then you have these several different kinds of these several different ways to create vertical permeability to allow brines to migrate upwards through the stratigraphic section into these areas where the bacteria are operating, where there's the highest concentrations of reduced sulfur. And yeah, that's it. So thanks for listening. And there's my email if there's any questions for me anytime later.
Alrighty, fantastic. I'm gonna hop back in here for the Q&A section. As previously mentioned, if you have a question, please submit it. There's a Q&A button down below. One of the questions I have, Billy, are you familiar with the work of Jillian Banfield regarding low temperature bacterial sulfide fixing at the Piquette mine near Tennyson? If not, we need to talk.
So I'm not familiar with that, so I guess we need to talk. Yeah, probably. Yeah, this mechanism though for bacteria, yeah, sulfate reducing bacteria fixing sulfide minerals though, I mean, like people have shown this to be operating at tons of deposits around the world, so I'm not surprised to hear about another one.
Alrighty. We had a question regarding the St. Peter and Prairie du Chien sulfide deposits, but it looked like you answered the question already in your presentation, which is great. Where was Southwestern Wisconsin mine that closed in 1979 located?
Yeah, so I believe that was in the Shullsburg area. Or yeah, sorry, did you have a answer to
No.
that too? Oh yeah. Yeah, so Shullsburg area in Lafayette County, this is where the largest known zinc deposits were found. And so these generally lasted the longest, in the face of competition from elsewhere.
Fantastic. I have, what would the bacterial colonies have looked like? Did they form mats that read in the rocks in the way algae mats show in stromatolites? Forgive me if I
Oh yeah,
pronounce that wrong.
stromatolites. So that's a good question. So the bacterial colonies, like I guess, yeah, let me so those were the biofilms that I had shown that were forming around the framboids, or I guess the framboids were forming inside of these biofilms. So they're kind of this like weird web-shaped structure that I'll go back to. Yeah, so these sorts of things. So it's like, it's these really creepy, kind of nasty looking web of a biofilm that forms these like this porous net, that then the pyrite crystals are growing inside. And kind of like so yeah, generally these are too small to see with your naked eye. It's not like a stromatolite where you'd like look at a rock and be like, oh, framboids are in there. But I mean, when you see large concentrations of sulfides, generally they're contained within them. Just like it's not something you're going to be able to see with the naked eye. Yeah.
Okay. Did you map the area of the Blue River near Willow Springs where the first lead smelter was located in an area east of Snow Bottoms?
So I did map the area east of Snow Bottoms. I'm not familiar with Willow Springs or the first lead smelter, so you should send me an email about that. I'd be very interested to hear about that.
Okay, I have two questions from the same person. First one, are some of these bacteria being used to create man-made sulfides or other minerals today?
Yes, so I'm not aware of them being used to like create a deposit necessarily from like shoving a bunch of bacteria down a well and like creating a deposit from brines today. I don't think anybody's doing that. But I do know that using sulfate reducing bacteria to fix metals out of solution, I think it has been proposed as like a way to clean up like acid mine drainage, like to fix metals that otherwise would be harmful to the environment. That's an
Um,
interesting question.
well, there's a second part. Are there minerals or deposits that the energy industry might be interested in mining in Southwest Wisconsin today?
So, I mean, short answer, I don't know. I mean, a little more speculation though, probably not, because just the size of these things and the commodities that they contain. So, I mean, if you're just interested in lead and zinc, like, I mean, that's basically all they have. They don't have a lot of the byproducts that add value to a lot of other deposits. Like they're not high in precious metals or things like germanium, stuff like that. And then, you really just can't get around that. They're just not very big. I mean, we're talking like, these things are like 1/100th the size of some of the big modern deposits that are coming online for those same sort of commodities. But yeah.
Is there a connection between the sulfide mineralization and dolomization of the Paleozoic rocks, or are those different events? Or is it still being researched?
That's an interesting question. So what I've read, I mean, I guess this is something that's still being researched, but what I've read is that the dolotomization occurred separately and before the main episode of sulfide mineralization, and then obviously that affected the sulfide mineralization event because, um, you know, the big lead and zinc deposits, or yeah, I guess the big zinc deposits especially are found where the rocks are not dolomitized. They're where they're still limestone because that makes them more reactive to acids and like. Anyways, yeah. Hopefully that answers the question.
Is your mapping going to take you beyond the Highland area once you are done there? And how much longer do you have there for your work?
So yeah, so I'm proposing a new mapping project to do the same sort of deal for the two quadrangles. So, same sort of area, but just shifted um, just east of what I previously mapped. So this basically fills the gap between Highland and Dodgeville. Um, and this work is totally completed. And this is a great segue because we just published this map and accompanying report on the survey's website, just this last Friday. So yeah, check it out if you want to learn more. Yeah,
Congratulations.
it is fresh.
How much barite and other non-lead zinc elements are you seeing in the Highland area?
Yeah, that's a good question. So barite, this is something that's found in certain areas of the overall lead zinc district, but is not found very much in the Highland area. And yeah, let me go back and show you my map of the ore deposits. Yeah, so in terms of other non-lead zinc elements, so this is another area that makes the Highland sub-district kind of special because if you can see these kind of turquoise stars that I put in there, those are areas where there's copper associated with lead and zinc, which is something that's kind of unusual. And, it's kind of similar to barite in that only certain areas of the overall mine district have that. And Highland just happens to be one of these things, or one of those places, I should say.
Fabulous. Okay. You focused on primary sulfide mineralization. How much evidence of secondary supergene mineralization do you see?
Yeah, so so I guess just to let everybody know, so supergene mineralization is what happens. This is like mineralization that's the result of weathering. So it's like these ore deposits were formed when these rocks were very far below the surface, and sulfide minerals are not stable at the surface. So when you expose them to air, they weather out and oxidize. And then sometimes, depending, they'll leave the lead and zinc behind, and that's how you end up with a supergene deposit. And to answer your question, supergene deposits are widespread here. I mean, basically anything above the water table has been completely weathered out. And this is how you get Instead of being a zinc sulfide deposit, it will be a zinc carbonate or smithsonite deposit, also known as like dry bone by the miners. And yeah, that stuff is widespread out here because a lot of these ore deposits are above the water table.
Okay, if anybody else has any additional questions, please add them to the Q&A function. Billy, if you wouldn't mind sharing your last slide there that has your contact information in case anybody has additional questions to send to you, that would be fantastic. There it is up on the screen for everybody. Otherwise, it looks like I'm not seeing any additional questions at the moment. So I think that about wraps it up here. Thank you so much, Billy, for answering our questions and for giving that fantastic presentation. It looks like a lot of people really enjoyed it.
Awesome. Glad to hear it. Yeah, thanks for having me.
Yeah. So thank you, everybody. I hope you have a good rest of your evening and happy St. Patrick's Day. All right. Goodbye.